Thank you very much. Can you hear me well? Well, thank you, Reginald, for such a nice introduction, and thank you to the organizers, Matthias and everybody, for such a wonderful conference, and Josh for contacting me with the organizers. Very happy to be here in Bern. I love Switzerland. It's my first time. Actually, I noticed that can I share if I share my screen, will this work? Yes, and does the clicker work? Perfect. So funny, the logo is a mountain, an uphill, and the logo of my channel is also a mountain because I grew up in the mountains of Colombia. So when I look around and I see mountains, I feel right at home. So I'm very, very, very happy to be here. And yeah, I'll tell you about attention mechanisms, and I call it celestial mechanics because I like to see words flying around. I don't like formulas. I just like to see images that move. So let's talk about a transformer. Right, a transformer is the reason we're here, because this thing started to work and started to talk really well. When I imagine a transformer, I just imagine something like Optimus Prime, right? And it generates text. Now, this drove me crazy when I first saw how ChatGPT works. It's very simple, but it drove me crazy. It generates text one word at a time. So, for example, if you give it a sentence, hello, how are you? It doesn't start talking. It just goes, the next word is probably the word doing. And if you want it to talk for a long time, let's say you say write a story, it doesn't write a story. It just goes once, because a story probably starts with the word once, and that's as far as it goes. If you want it to keep going, then you have to say, okay, now, write a story once. And it goes, sounds like you have to put the word upon. Just feels like the next word. And it just keeps going like that. And somehow that talks. So this generating one word at a time, I found it interesting. I didn't think that's how we were going to get a chatbot. I knew for a while we needed a chatbot. Everybody knew that when AI started working well, and I started guessing things, understanding if I email spam or what's an image or something, everybody knew we needed a chatbot. But generating one word at a time is very strange. And it's also not a new concept. I mean, this generating one word at a time already existed in WhatsApp or in any text messaging. You would just guess, you put something, hello, how are, and it'll guess not one, but 3 words. This is supervised learning, right? It answers a multiple choice question. What's the next word among all these options? That's supervised learning. But somehow, if you repeat it many times and you keep asking that question, what's the next word, the thing talks. But we had this, right? We had a ChatGPT. This uses a neural network that just gets used to the input and what's a common output. I don't know if you've ever tried this. Try to use the WhatsApp autocomplete like a chatbot. I tried this, and I start pressing the middle button, and it goes, hello, how are you feeling this week, and your kind wishes for a wonderful weekend with your kindness and happiness for your family, love, and This is from my text. I don't know if I'm that nice when I talk, but it makes no sense, right? It doesn't carry context. However, if you look at it with a small window, it does make sense. I mean, if you look at every 4 words, hello, how are you feeling? And happiness for your, every 4 or 5 words make sense, but the whole thing doesn't. So it's like a person with a really low attention span talking, right? It just doesn't carry a story, but it does make sure every 2 or 3 words fit well. But clearly we need something more advanced. So this was ChatGPT's grandpa. We just need a better version that actually talks, but nothing there is new. And some things made it better. Computers got bigger, so we can have bigger neural networks with trillions of parameters. There's more data. Now everything we do generates data, so there's a lot more. But there was one advancement that actually kind of made it cross the line, and it was attention. So attention is what I'll tell you today. It started in this paper called Attention is All You Need by some people from Google. And that's really what started giving these models a way to understand context. So attention appears here in the transformer architecture. This is an ugly drawing. But really what happens is that this blue part, the feed forward, that's the WhatsApp next word generator. Yeah, that's the neural network. This yellow thing is the attention one. And then this other pink thing over here is an embedding. So I will talk a lot about this yellow part, the attention, and also about the pink one, the embedding, because embeddings are important. But basically, the way I see the attention mechanism is if ChatGPT was the DeLorean from Back to the Future, the attention would definitely be the flux capacitor, the one that makes it travel in time. I am aware that this is a reference that reveals my age. For the younger crowd, if ChatGPT was Iron Man, then this would be the attention would be the arc reactor. So anyway, before I get to attention, let's start with embeddings. Because I know I sold attention, but actually the most important thing, not just in, I would actually say that in most fields of machine learning, embedding would be the most fundamental thing, because that's when things get translated, right? When you translate from human speak to computer speak. We speak in words, and computers have no clue what a word is. They only speak in numbers. They don't even know what hello means. They just speak in numbers, and they do wonders with numbers. And we need a good bridge between them. We have no choice. And this bridge is called the embedding. And the better an embedding is, the better the model is. 10 years ago, embeddings were bad, and some things like spam detection were hard. Now embeddings are so good, and those problems are really easy. So if embeddings get better, 10 times better tomorrow, I assure you language models get 10 times better tomorrow. And what's an embedding? Well, it's a translation from words to numbers. So it's basically a word gets sent to a bunch of numbers. I like to see things as drawn in the plane. So let me make you the first quiz of the day so we wake up, okay? It's an easy one, don't worry. I have a bunch of words on the screen, a football ball, some strawberries, a car, and houses, etc. And each one has coordinates, right? So like, for example, tennis is 1, 5 because it's 1 horizontal and 5 vertical, right? The question I have for you is, where would you put the word apple? And I'm going to give you 3 options, A, B, and C. So show of hands, who votes for A? Who votes for B? Who votes for C? Great. Okay, we have almost consensus that I would also put it at C. Why would you put it at C? Who can tell me quickly? It's a fruit. Fruits should stick together, right? The least I can ask of an embedding is that it puts a fruit with the fruits and not with like a castle, right? That makes sense. That's the least I can ask of an embedding. Well, yeah, turns out that that's a very important thing of an embedding. Words get sent to numbers, but similar words get sent to similar numbers. Now, I did a nice small embedding that sends every word to 2 things, but in reality, embeddings are much bigger. You can send every word to lots. I've seen all the way to 4,096. But in general, the ones I've seen all over the place are 1,024 or a few hundred, where every word gets sent to a bunch of this. As a matter of fact, you can send longer pieces of text, and similar sentences get sent to similar things. But today, we're only going to worry about words. And the way I actually do like to see embeddings is, imagine if you could describe a word with 1,000 numbers. So in my head, as a human, I would think that maybe one number is color, the other one is size, maybe flavor, whatever it is. But this is done with a neural network, so a lot of the properties, we can't even tell what they are, but the computer knows. But imagine there are 1,024 properties of the word, and that's the description of the word. And so if I have the word apple and the word pear, they're similar descriptions, so they probably have similar, this is an embedding vector, the list of 1,024 numbers attached to each word, okay? So, okay, we did well, you did well in the first quiz. So now I have a second quiz. The second quiz, here I have a strawberry and an orange, and here I have a phone and the Windows logo, okay? And now you're gonna tell me top left or bottom right. And you can just yell the answer, okay? Or point or whatever. Okay, so where would a cherry go? Good job, top left. Where would an Android go? Do it with the energy that Reginald was talking about. Android, bottom right, thank you. Where would laptop go? Thank you, bottom right, good job, you're rocking this. Banana. Top left. Top left, great. Apple. Half of the people say top right, the riot starts. Yeah, we don't know. We don't know where to put Apple, right? Because we don't know if we're talking about a fruit or the technology company. And there's no embedding that will know this. If some scientist comes up with the best embedding tomorrow, it's still not going to know because it's a problem with the language. Like, because a human wouldn't know. If I stand in front of you and I say Apple, you won't know what I'm talking about, right? So the best it can do is maybe put it in the middle or somewhere. We don't know. And so we have a problem. And we need to solve this problem. So what would you ask me if I say Apple, what would you do to try to find out what I mean? Context is exactly the word, right? You would wait until I say more stuff or see what I've been saying. And if I've been talking about computers a lot, you know this probably. So you have to look at the other words around. That's what we're going to do. We're going to look at the other words around. And that's exactly what attention is. You look at the words around and you do stuff with the embedding. Okay? This is the formula of attention. Ugly diagrams with ugly formulas. But today we're going to learn this. This will make sense today, I promise. And this one too. But I like to look at this way. Okay, now you're going to help me out. Now I have a sentence called, please buy an apple and an orange. Now you know what I'm talking about, right? Talking about a fruit. And if I say Apple unveiled a new phone, you also know what I'm talking about, right? Now help me out. Which word gave it away in each sentence? Like what? This would be phone, right? And in the first one? Orange, right? It's not buy, because I would go buy a phone, right? It's not please, it's not new. It's orange and phone. So we're going to have to figure out how orange injects something in Apple and brings it or something, or pulls it. And it literally pulls it. Like the way, imagine that this is the embedding. There's your orange, there's your phone, and your ambiguous Apple is in the middle at the coordinates, I don't know, 6, 6 or something. And we say, please buy an apple and an orange. So orange pulls phone. And what I mean by that is that it draws a line and literally pulls it, right? Literally, the apple falls towards the orange. And if I have the word phone, then the phone pulls the apple. So it falls towards the phone. So it's kind of like gravity, right? And I had to have apples if I talk about gravity, because Newton, you know. Actually, all these things connect, because do you know why Apple's called Apple? So the first logo of Apple was Newton with an apple falling. So there's the connection of the 3 apples and the gravity. But it is literally gravity. The words move around in the embedding. And basically, you're just changing the embedding, right? Like the embedding here for ambiguous apple is like 6, 6. But when I say the word orange, then it's changed to like 8, 8. Okay, so now the computer thinks of Apple in a different way. So we're modifying the embedding given the context, okay? But here's something, we kind of cheated, because we said the word orange is important, but that's because we're human. We know that orange is related to Apple, but the computer doesn't know. For the computer, as far as it's concerned, please also pulls Apple and also pulls Apple. So how do we fix this problem? Well, it actually we have to pretend that all the words pull Apple, because we just don't know. So this becomes a mess, because Apple gets pulled in all directions. But what can we do? Well, luckily, in an embedding, similar words get sent to similar numbers. So close words get pulled more than far away words. Like gravity, like planets, right? Or like magnets. If I have a magnet that's close, it pulls more than if I have a magnet far away, right? So the apple and the orange are close. They pull themselves a lot. And apple and buy are really far. So they pull very, very, very little. So you apply attention to all the words. Apple pulls orange and orange pulls apple. And they barely pull the far away stuff. And that's how you solve the problem that's how the computer knows that orange is the important word there, by which one is the closest. And so I see it like celestial mechanics, right? Like the Earth and the Moon pull each other a lot because they're close, but like Saturn doesn't really pull it because it's really far away. So if you imagine words flying around and gravity, that's how I see attention. So for example, if I say apple, but I've been talking about fruits for a while, then there's a strong galaxy of fruits. And whenever I say apple, it just gets pulled. And now the model knows that very likely I'm talking about a fruit. So let me get a little into the formula, because I promise we're going to understand the formula. The formula for gravitation is mass 1 times mass 2 divided by r squared. We learned in physics in high school. It's not going to be that. It's going to be this, that pulls the Earth. It's going to be something like this. Softmax qk transpose divided by square root of dk. We'll see all these things. And basically what happens is that you cut a bit of apple and put that amount of orange. And you cut the right percentage, right? So, oh, sorry. I'll say more about that later. But basically, if you imagine that a percentage of the apple orange gets put into the apple, and now we have an apple orange-ish, that's what's happening. And in the embedding, it's just moving around, okay? But before I get to more of this, let's talk about something called similarity. Because I've been talking about distance, but kind of cheating. Distance is not as the important thing. The important thing is similarity. But they're very similar. So if I have in the embedding, and I have a pear and an orange close together, and Android is really far away, then my similarity means they're close. But there's actually a measure. That's a high number if you're close, and a low number if you are far away. So show of hands, who's familiar with dot product? Oh, right, a lot of people. How about cosine distance? Great. Well, I'll say them again. But it's good that you know them. If you haven't seen them, don't worry. We'll see them here for the first time. I'm going to come up with a number that is high when the two words are similar, and it's low when the two words are different, okay? So here's our embeddings. By the way, in the embeddings, I told you that things mean something, right? Because this horizontal H, it kind of means fruitness, and the vertical H means technology. So the more technological the word, the higher it is. The more fruity the word, the more to the right it is. I'm very optimistic with my embeddings, but bear with me. So my coordinates for orange are 6, 1, and my coordinates for pear are 7, 2. Notice that the big number here is at the same place as the big number here. I want to get some advantage from there. So what I'm going to do, and here the opposite happens. The big number here is not correspond to the big number here. So I'm going to get a big number from here and a low number here. Here I multiply the numbers in the same column, and I get big times big, 6 times 7, and 1 times 2, and I add them. That's the dot product. If I do the same thing here, I get 6 times 1 plus 1 times 8, and this is smaller because the big numbers don't match, right? And so here I get 44, and here I get 14. So if I do that, if I take two vectors and I multiply each coordinate, if they're similar, I'm matching big numbers, so I get a big number. And if the numbers are different, then I get something small. So that's dot product. A large dot product means a large similarity. A small dot product means a small similarity. And then I have a cosine distance, which is a little different. But I don't measure how far things are. I measure how much the angle they make. And so Android and pear make a big angle. So I take the cosine, I get a small number, a small cosine. And apple and orange, and pear and orange have a small angle, so a large cosine similarity. So in other words, I don't look at the distance, I look at the angle they make. Now, here's the question. Has anybody stopped to think, why are we using angle instead of actual distance? We have a perfectly defined distance. Why do we use the angle instead? Or maybe better, where in the world would somebody use angle instead of distance? Like, how nerd are you to actually look at an angle instead of measuring? Where would you do cosine distance in the world? Not in machine learning. What? Yeah?
It's normalized on the globe.
The globe, exactly right. In the world, we don't use distance. We use cosine distance, right? Because if I want to measure the distance between 2 points, I don't open a hole in the earth and walk directly. I look at the angle, and that's the distance between 2 points. If you're close, it's an approximation to say you're close. But you wouldn't say we're not 10 meters away. We're 10.001 according to the curvature of the Earth. You'll start losing friends if you say that, believe me. But basically in the world, we use cosine distance. And that's the thing. Embeddings look more like the world than like the universe. Okay? This is way too optimistic. But embeddings, I lied when I say they look like that. They look more like this. Nothing is in the center. Nothing is sent to 0, 0. And stuff is all over the place. This is a lot of mountains and a lot of valleys, but they look like a sphere with a lot of spikes and a lot of holes and stuff, but they can be treated like a sphere. And that's why we do angles instead of actual distances, okay? So for example, Google Maps distance is exactly angle distance, right? Have you ever happened to, it tells you you're right beside somewhere, but that somewhere is 100 floors above in a building, but it tells you you're right there? That's because you make a small angle with the center of the Earth, right? And that happens in embeddings. You could have words like bad and atrocious, for example. Atrocious is like an exaggeration of bad. And if you look at embedding vectors, they tend to be much higher. But how do you tell that bad and atrocious are similar? Because they make a small angle with the center. So cosine distance in embeddings is much, much better. And why did I say dot product and cosine distance? They're almost the same thing. If you're in a circle with radius 1, they're exactly the same thing. And if not, you just divide it by these lengths, something like that. So sometimes I will use cosine distance, sometimes I will use dot product, and sometimes I will cheat and say distance, but I mean the same thing. And if you have, the word with itself, the cosine distance is 1. If they're orthogonal, means completely unrelated, the cosine distance, the dot product and the cosine distance is 0. And if they're completely opposite, then it's -1 for the cosine distance. Which one does ChatGPT use, dot product or cosine distance? It actually uses a completely different one, but, well, not completely different, very similar. That is called the scale dot product, which is take the scale dot product and divide it by the square root of the number of entries in the embedding. So if you have an embedding of 2 entries here, two dimensions, you divide by square root 2. If you have 1,000 dimensions, you divide by the square root of 1,000. So it's dot product divided by the square root of the number of entries in your embedding. Why? Because that's what worked. That kept the numbers at a reasonable size. There's really no other reason. And so now we have part of this formula, right? We have this, I haven't told you what K and Q is, but we have a product here divided by the square root of the number of entries in the embedding. So we're somewhere there. We need this now, right? Okay, so now let me explain to you how this thing moves around. What we really want to do is we want to turn the apple into some percentage of apple plus the remaining percentage of orange. And the more similar they are, the more orange there will be in this equation. These always have to add to 1. So how do we do it? Well, let's say the similarity between apple and apple is 1, because they're very similar. And let's say that between apple and orange is 0.7, because they're pretty similar. So what we're going to do is the new apple orange is 1 times apple plus 0.7 times orange. Those are not, we're not done yet, because these numbers may be negative. We may have a negative similarity. I don't want negative numbers. What do you do when you want to turn negatives into positives? You could square, but I also want small numbers to go to small numbers and big numbers to go to big numbers, right? So -5 would go to a big number. So the next thing we do is raise e to the that, right? So instead of 1, I take e to the 1. Instead of 0.7, I take e to the 0.7. And now I have this. My new apple orange is e to the 1 apple plus e to the 0.7 orange. But I want them to add to 1. Any ideas of what can I do to make them add to 1? Oops, sorry. I could just divide by their sum, right? I could just divide by this sum of the numbers, and then they have to add to 1. And that's how I got my percentage, 57% apple plus 43% orange, okay? And there we go. That's called the softmax. If you've ever seen softmax, that's it. You raise e to the everything and then divide by the sum. And so now we have this formula, right? Softmax divided by the square root of the k. I'm missing this part. I'm missing the k and the q. By the way, any questions so far? Oh, I'll say one thing and then I'll ask a question. If you have a high similarity, these numbers are high. There's a lot of orange going into the apple. If you have a low similarity like truck and apple and you do that formula again, you just get a very, very small percentage of truck added to apple. So it moves very little. That's like when Jupiter pulls you, so far away that it barely pulls you. Okay? So now we have this part of the formula. Now I need to tell you what is K and what is Q. What is the key and the query matrices. So here's a small problem. So far, I've used similarity as like distance in the embedding, and it seems like a good thing, but it has so many problems. It has way too many problems. And we need to fix them with the key and the query matrices. Now, matrices is some a big word in linear algebra. You can think of them as arrays of numbers. I don't like to think of matrices as arrays of numbers. I like to think of them as something different. I think looking at a matrix as an array of numbers is kind of like looking at a book as an array of letters. You're kind of missing the point. You can't just be like, well, there's a lot of E's and a lot of... there's just something behind, right? There's a story behind every book. Well, there's a story behind every matrix, and the story that I like to tell with matrices is linear transformation. So I don't think of a matrix as numbers, I think of it as linear transformation. What's a linear transformation? Well, let's say I have an image of a dog. I could do several things to this image. I could rotate it, that's a 2 by 2 matrix. I could stretch it in this direction, that's another matrix. I could stretch it in this direction, that's another matrix. And I could do something called the shear, which is when I leave in a book, I put the bottom on the table and I push the top, and I get something like this. That's another matrix. And any combination of these is a matrix. So if I think of sending a square to any parallelogram, that's a matrix. If it sends it to a circle, that's not a matrix, okay? So only parallel lines go to parallel lines. And that's how I like to see matrices. And why did I have to go through all that? Because sometimes, let's say I have an embedding, where this embedding I have size is towards the right and how much animal you are goes to the top. Sometimes you're not going to want that. Instead, you're going to want this. Okay? You're going to want to modify your embedding to get something better. Why would I want to do such a thing? Why would I want to modify my embedding? I'm going to give you 3 reasons for that. Okay? The first one is that not all dimensions imply similarity. And for that, we're going to have another quiz. But this one's more conceptual. And this one you have to show your work because every solution works. But I'm going to give you 3 embeddings. Okay? And as you can see, things get big when they go horizontal and more animal when they go up. So I have animals on the top and big stuff on the right. Which one do you like more? And this is a conceptual question. Take it as you like. Which of the 3 do you prefer? You prefer the third one? Okay. Why?
Most animals is kind of binary.
Oh, that's a good one. Yeah. Animals is binary, so we have all the non-animals here and all the animals here. And size is more descriptive. So that's a really good answer. I have a different one. Any others? Any other takers? So, you like the second? Yeah. Perfect. Yeah. I actually like the second one too. So there's an argument for all of them, like the one you had. But I like the second one more, and I'll tell you why I like the second. This is purely my opinion. I like, but you're right too that this one's good. So don't. This is purely my opinion. I like this one more because in my head, a rabbit and an elephant are more similar than an elephant and a truck, because they're both animals. If I'm talking about elephants, I may bring up a rabbit, but I may not bring up a truck. If I'm trying to fit things into a ship, I need the elephant and the truck to be more similar, because they weigh similar. But if I'm in a conversation, in my head, I think I'm talking about animals, I keep talking about it. So I kind of want these 2 to be more similar than these 2. So in my head, this is the better one, right? So I needed to do a linear transformation, right? Sorry. Oops. I needed to do a linear transformation for that. Give me 1 second here, please. And what's the linear transformation? Well, what I'm going to do is I'm going to make the size a smaller thing. So I'm going to take the size and multiply it by a small number. For example, 0.3. So my 1.1 and 1 become these smaller numbers. And I'm going to keep the animalness the same, And so I shrink this embedding like this. And now the elephant and the rabbit are closer. Because maybe size is not so decisive when you want to tell if two things are similar or not, right? Maybe animalness is more descriptive. So I've modified my embedding so that I get better similarity. Okay, and if you're curious, this is the matrix that corresponds to that. So I've turned it into this, right? So I did a modification to the embedding to get one that describes similarity more. All right, we have a second reason, and it's that sometimes you need to combine dimensions. So I'm going to give you another quiz, and in this one, I'm going to describe an embedding that's a pretty unforgiving embedding. In this one, we have two very smart kids, Aisha and Beto, and we have an embedding where one dimension is if math is your favorite subject, okay? And the other one is if physics is your favorite subject. And her favorite subject is math, and his favorite subject is physics. And so the embedding basically puts her here, and it puts him there. And that's a pretty unforgiving embedding, right? Because imagine if you like math a little more, but then one day you start liking physics a little more. You made a small change, but it put you all the way from there to there. That's not good. You want things to change a little if you change your data a little bit. So what we're going to do is we're going to modify this embedding. But now I'd like to ask you, which one of these three do you prefer? And again, this is a purely conceptual quiz. We may differ. But out of these three, which one do you think is the better embedding?
Second one.
The second one, right? I kind of like the second one too. And again, this is up for a conversation. But in my head, the two kids are very similar if one of them loves math and the other one loves physics, right? So I want to make this embedding a little smoother, a little kinder with respect to small changes. And so I do my combination. And what I do is this. I don't want these kids to be so far away. So I'm going to basically put a little bit of math in the physics and a little bit of physics in the math. I'm going to say that if you like math, you're going to like physics a little bit. Okay? So what I'm going to do is I'm going to say, if you like math, one, you like math here. But if you like math, you're going to like physics 50% at least. So I'm going to add 0.5 to your physics is your favorite score. And I'm going to do this, and that moves her 5.5 units to the top. So she's closer to the kid. And then I do the same thing with Beto. I take the one of physics, and I say, if you like physics, you like math 50%. So I'm going to put you here, and I move that kid over there. Now they're a lot closer. And the transformation is actually this one over here. The math goes to math plus a half of physics. Physics goes, this becomes this. Physics goes to physics plus half of math. So it becomes this. And then that square becomes this parallelogram. And the plane follows, right? The whole plane becomes a parallelogram. And that's the linear transformation. And this one is just better because the math kid and the physics kid are close, okay? So that is the second reason. So I've given you two reasons. One, that embedding, that dimensions sometimes don't speak so loud in terms of similarity. The second one is that sometimes you need to combine different dimensions. The third one is the weird one, okay? Just like in gravity, as a moon and Jupiter don't pull each other the same way. Jupiter pulls the moon more than the moon pulls Jupiter, right? The sun pulls the earth more than the earth pulls the sun. And the same thing happens with words. The pull doesn't have to be symmetric. One word can pull another one more than the other one can pull the first one. And I'm going to ask you, what do you think? So it's in an embedding, the pull is based on distance, but I want a stronger pull for one direction. And I'm going to, just like with planets. Now I'm going to ask you, what do you think? If I give you two words, I'm going to give you fisherman and net. Which one do you think pulls more? Fisherman pulls net or net pulls fisherman? Good. Why? Sorry? Exactly. Yeah, that's good job. Fisherman pulls net a lot more than net pulls fisherman, because if I'm talking about a fisherman, very likely I'll be talking about a net. A net gets pulled. But if I'm talking about a net could be a badminton net, a tennis net, the internet, all kinds of nets. And if I'm talking about a net, it's not so likely that I'll bring up a fisherman in the conversation, okay? So it's interesting because it's the small word that pulls the big word. Net is a bigger word, but the small one pulls it more. And so just to give you another example, there's a movie called The Fisherman. I assure you there's a net in that movie. There's a movie called The Net. I assure you there's no fisherman anywhere in that movie. So in other words, yeah, we have a stronger pull from fisherman to net than from net to fisherman. But this is where keys and queries come in. The puller is the key, and the pulled is the query. But unfortunately, there's not a ton we can do with one embedding, because if I have an embedding, for example, in my embedding now, horizontal direction is how much fishing there is, and vertical is how much technology there is, then there's no way, even if I modify it in the smartest possible way, the pull is still based on their distance. So I need an asymmetric pull. So I can't do it with one embedding. So what can we do? Well, we can't do one transformation. We have to apply two transformations. One for the puller and one for the pulled, okay? So this is what I'm gonna do. I'm gonna do a little bit of magic, but then it will make sense, okay? One transformation is for the keys, the one that pulls, and one is for the queries, the ones that get pulled, and I'm gonna calculate the angles from one from there and one from there. So I'm gonna do it first with angles. It's gonna look like magic, I warn you, but then it will make sense. So this is what I'm gonna do. I'm gonna calculate the pull of how much fisherman pulls net. So I'm gonna take the angle between fisherman in the keys and net in the queries. That becomes this angle. It's a slightly big angle, so they're not that similar. And now I'm gonna take the angle between net here and fisherman here. And well, we get the same angle, so I haven't done very much. But now check out what happens when I apply linear transformations to the keys and the queries. I'm gonna apply this transformation to the keys. I'm gonna compress it like this. And then I'm gonna apply this transformation to the queries. I'm gonna compress it like this. And now I'm gonna look at the angle between fisherman there, fisherman is the key, and net here, the query, and look, I get a 0 angle. They're very similar. And when I do fisherman on the, net on the left for how much net pulls fisherman, and fisherman here, I get a big angle, so that's not good. So I need to modify them in a different way. So I mean, that is good, because I have a weak pull here because I have a lot of similarity, a strong pull here because I have a lot of similarity, and a weak pull here. So that's how I did it. This looks like magic. So to finish up, I have 5 minutes, I will give you an example with embeddings. This one over here is me, and I'm a huge fan of Taylor Swift. I don't know if you know this about me, but I'm a huge fan of Taylor Swift. I'm going to ask you a question. In the embedding, which one do you think pulls the other one more? Who thinks I pull her more? Who thinks she pulls me more? Actually, it's counterintuitive. I'm the fisherman here. I'm the smaller word. I pull her way more than she pulls me, even though she's bigger. The reason is this. Think about this. If I'm always talking about Taylor Swift, and I'm always going to the concerts, and I have the posters in my room, and there's a conversation about me, people will be like, hey, where's Luis? Well, he's at the Taylor Swift concert. She comes into the conversation, that's about me, very likely. On the other hand, if there's a conversation about Taylor Swift, I don't think I'm gonna appear in that conversation. So she does not pull me, but I pull her. You see what I mean? So now we have to work out the embedding for that. Okay, so I have a stronger pull, she has a weak pull, and so I'm the smaller planet, but I pull the big planet more, because the smaller word pulls her more. So let's do a very silly embedding. This is a silly embedding, right? One entry in the embedding is if you are a fan of Taylor Swift. I have a 1 for that because I'm a huge Swiftie. And the other one is if you're a Lewis fan, so I'm a fan of me, so, you know, I have a 1 there. And the other one is, are you Taylor Swift? So everybody has a 0 except for Taylor Swift. It's a silly embedding. And are you Lewis? So I'm the only one with a 1 there, and everybody has a 0. And let's see what's for Taylor Swift. So she's definitely a Swiftie. I'm rounding this up to 0.01, even though it's a 0. This is 0.1 with a 1% margin of error. But I want some numbers for my equation, so I'm going to put a 0.01. She is Taylor Swift, so there's a 1, and she's not Lewis, so there's a 0. Is this clear? The embedding is clear? Okay, so if I do dot product, what happens? I multiply each column, so I have 1 times 1. I don't want this because that's a strong pull. The fact that we're both fans of Taylor Swift means nothing in how she would pull me. So I don't need to match. The dot product doesn't work. I need something different. So what matches from the top and the bottom, right? How much I pull Taylor Swift? Well, 2 things say how much I pull Taylor Swift. The fact that I'm a Swiftie and the fact that she's Taylor Swift. You see, if these 2 numbers are big, then she pulls me. I pull her because I'm a fan and she is Taylor Swift. With someone else, this is a 0, so they don't pull me, you know? So I need that product. And if we're going to do how much, this is the key on top, and that's the query. If I'm going to do the opposite, like how much she pulls me, well, we'll look at how much she's a Lewis fan, very little, and how much I'm Lewis, and we want to multiply these 2. So it's a twisted dot product. You don't just do row by column, you do this with that and this with that. That's the keys and queries, and that gets a 0.01. This is a more believable embedding. It's likes pop music. I have a 1. Likes machine learning videos. I like machine learning videos. Makes pop music. I don't. And makes ML videos. I have a 1. And then she has likes pop music 1, likes ML videos. Maybe she likes them or maybe she doesn't have time to see them, but it's 0.01. Makes pop music 1 and makes ML videos 0. So the pull is from how much I like pop music and how much she makes pop music. When this happens, there's a pull. And in the other direction is how much she likes ML videos and how much I make ML videos. So those are the pulls, okay? And just to finish up, we have basically what we want is we have the keys, the pullers, and the queries that are the pulls. And I want to match these to this. That's the modified dot product that I want. I want the product of the first 2 plus the product of the second 2. So it's like a dot product, but from some stuff there and some stuff here. And for the opposite pull, then I have, if I want to see how much she pulls me, then we have her keys and my queries, okay? So that's what the keys and queries matrices do. They take your vector and they pull out the pullers, and then the other one pulls out the pull, and that's how it works. So for example, if you have a very long embedding vector, some of these are things that pull other words. Some of these get pulled. So for example, let's say she likes the Chiefs and the Beatles and American football. That means she would pull this guy. I think he's still the boyfriend, but I may have to modify the slides every now and then. He plays for the Chiefs. He likes the Chiefs. He plays American football. She likes American football. So she pulls him into the conversation. If she likes the Beatles, she would pull Paul McCartney into the conversation because somewhere he has an entry called "is a Beatle." And in the other direction, you know, anyone who's a fan of pop music gets pulled in this like this. And if you're talking about a Grammy, she has the Grammy winner, so it gets pulled. So basically, if you have an embedding vector of 1,000 entries, some of them are used for pulling other words. Some of them are used for being pulled. And what the keys and queries matrices do is they match the ones that are pulled with the ones that pull when the ones that are pulled in the other embedding vector. So as a little, I'm finishing soon. The key matrix tells us 3 things. What features are important when comparing words, what features need to be combined when comparing words, and what features pull other words, and what features make the other word get pulled. And I think now we have the formula, right? Because we have the KQT, that's the dot product with the K and Q matrices. We have the divided by the length of the vector, and we have the softmax. So that's attention. And with that, I would like to say danke, because I think I'm in my time period. So thank you very much. Thanks for having me here.